Yours is an isogeometric. It's just
I was not invited by them, so I was invited by Simona.
Hello, can you hear me? Okay, I'd like to see if I could start the afternoon session for our second plenary. I'm very happy to introduce Professor Tom Hughes. I took a little bit of his bio down. I'd like to say a few words also about how I first met Tom. But Tom's background, he started with his bachelor's and master's in mechanical engineering in Pratt Institute in New York. He subsequently went on to do an MSc in mathematics in Berkeley. Berkeley would be the UK pronunciation of somewhere else completely. As many of you will know, he's taught at Caltech, at Berkeley, and at Stanford, and is now at the University of Texas in Austin. I couldn't possibly go through all the prizes and awards you've received. You're a member of the US National Academy of Sciences, the National Academy of Engineering, and indeed a foreign member of the Royal Society for the UK side. I think from my point of view, I first met Tom in the late 90s when I had a very strong interest, as he did, in bioflows. So that seems very remote from initially from the topic here. He had a contemporary, I guess, of mine called Charlie Taylor, who's gone on to do some fantastic work using finite element methods in bioflow modeling. But the thing that struck me about that is the kind of key areas that he's moved into such an impact on. So there we go from the late 90s, early 2000s in bioflows, and then there's been a more recent wave in isogeometric analysis. So I guess that's what you're taught to today, and so if you'd like to welcome our next plenary speaker. Thank you, Tom.
Well, thank you, Spencer. I'm delighted to be here and honored to be here. I will talk about isogeometric analysis today, and I'm going to emphasize the analysis aspects rather than the design aspects, but it really is a subject that was born in trying to create some sort of a unification of both design and analysis. I'll say a few words about finite element analysis to begin with, because it's really the point of departure for isogeometric analysis. Then I will run over some of the basic ideas, some of the basic tools that are used, just to give a little bit of a primer to individuals who are unfamiliar with them. In the mathematical analysis of finite element methods, certainly functional analysis holds the day. It's considered the approach. But spectral analysis, which is widely used in finite differences, for example, has some great value, in my opinion, to shed light on finite element methods and isogeometric analysis finite element methods. They are finite element methods at the end of the day. With the ideas settled, I'll show some applications that will illustrate some of the key features of isogeometric analysis: wind turbines, simulation of prostate tumors, boiling, and then I'll talk about a fundamental problem which emanates from computer-aided design, namely TRIM, and the analysis counterpart of that, immersion, and an example there will be heart valves. So let's begin with finite element analysis. Everybody knows everything about it, I assume, in this audience. It's the absolute standard in computational structural analysis. One of the areas that it has revolutionized is crash dynamics. Cars are designed on computers nowadays for crash, and they are done with very, very intricate models, as you can see here. And if you look inside this Mercedes, you can see that there are actual dummies in there. Airbags have been deployed. There are anthropomorphic dummies, and they're becoming more and more realistic as time goes on. It's interesting to note that many things are analyzed for crash, and a particular thing that many of you have in your pocket involves computational models that are about 10 times as large as any car, and that's the iPhone. So, well, if you drop it, though, the glass will still break, unfortunately. Finite element analysis is not only used, of course, in structures. It's one of the main technologies for fluid dynamics. And I thought I would show this application and a few applications in the biomedical area. This is one that was done by Alberto Figueroa Alberto did his PhD with Charlie Taylor, and Alberto was a student in our group when I was still at Stanford. And as I mentioned to Spencer before, I taught a course on how to adapt a structures code, a fixed mesh structures code, to fluid structure interaction. And that became Alberto's thesis, and that was the coupled momentum method. But this is the type of modeling he's been doing these days, full body models with over 100 main arteries, as you can see here. This is fluid structure. It looks like it could be even a one-dimensional network type model, but in fact it's a detailed three-dimensional model of both the fluid and the structure. And the material properties of the artery walls have spatially varying properties. And this is kind of giving you the idea of the resolution of the mesh. This would be the surface mesh, your shell in essence. And inside there's a tetrahedral mesh of a similar refinement. So you're actually computing detailed flow features as well. And this is just an animation. You can see the arteries are moving. You have the velocities and the pressure distribution. And these are the types of models that you can use to study many things. This model has been used to study baroreceptor response. You can actually tilt the model and see the effect of inclination on blood flow and blood pressure. Another application, again, it emanates from the work of Charlie Taylor. Charlie was my PhD student. He and one of my former colleagues, Chris Ahrens, who was the chief of vascular surgery at Stanford, they started a company about 10 years ago, roughly, and it's called HeartFlow, and it's quite an interesting company. It's a so-called unicorn. It's privately held, but its capitalization right now is over $1.5 billion. And it uses techniques that Spencer mentioned. These are all stabilized methods from circa 25 years ago that we were developing, in particular for computational aerodynamics at the time, but also for incompressible applications like this. This is a tool, their main product is a tool to do coronary artery disease diagnosis. It's incredibly accurate. There have been many clinical trials. It was the first computational medicine technology to gain FDA approval, and it's now has reimbursement from Medicare and Medicaid in the United States. Actually, I think it has UK reimbursement as well now. So it is shown in every trial that you can compute these things and avoid invasive procedures that are somewhat risky, in fact. Now, with all those nice things, what's wrong with finite element analysis? Well, you might think absolutely nothing. But there are issues. There are some accuracy issues, I would say, and stability issues if you go to higher order. All of those approaches were done with basic linear elements, linear tetrahedral, linear wedge-shaped elements. In the case of the structures, they were quadrilaterals and bricks, but lowest order. In addition, in engineering analysis, what you do is you're doing analysis based on computer-aided design representations, CAD files. And you'll hear this from people that are like vice presidents of engineering, that they spend a lot of money on developing computational models, a lot of money and a lot of time. There was an anatomy of the process done at Sandia National Laboratories in the US where they do tremendous amounts of finite element analysis, both structures and fluids. And they attributed the fixing, the repairing of CAD files so that you can generate a mesh, and then the mesh generation itself to over 80% of overall analysis time. It's a major bottleneck in engineering design. In addition, the simplifications sometimes that you induce to make a meshable geometry, you get rid of many geometrical features. And my attention has been drawn lately to a number of applications where the major errors in the analysis are due to geometrical simplifications. So these are shortcomings. So a while back, about the time I was transitioning between Stanford and University of Texas, I decided to take a look at this problem and see if something couldn't be done. But first, let me just say a little bit about why it's so time-consuming to create finite element meshes from CAD. This is a simple example. This is just a part. This is a B pillar in a Honda. as you can see here. It's just a piece of sheet metal that's been bent, cut, and some holes have been drilled in it. One piece of sheet metal. Now that's the visualization of it. That's what you see, and that's what you get from computer-aided design. But in fact, when you want to build a mesh, you have to go to the data structure. And what that consists of is actually 1,280 trimmed surface patches. These are tensor product patches that are cut with trim lines, and where these things intersect, there are gaps and overlaps. They don't fit together. All that has to be fixed to generate a mesh, so it's not watertight. So that gives you some inclination that simple things within computer-aided design are very, very complex, and when presented to finite element analysts or mesh-generated people, there's a lot of work to be done just to get it prepared. So with an objective to fix all that, the approach that I took was to try to reconstitute finite element analysis more within CAD geometry, closer to CAD geometry. It's interesting, historically, the finite element analysis was developed and commercialized way before there were commercial CAD programs. So it was fixed. CAD came along. It needed different representations to do the job. So these things have been developed very, very independently. So it seemed to me that if finite element analysis had been developed after CAD had been widely available, it might have had a different form, and I decided to try to embark on that path. And if you do such a thing, the idea would be you could simplify finite element model development, which is, in some sense, the big problem, and then integrate design and analysis. And that's what isogeometric analysis is all about. So we wrote a paper in 2005, and if you look for citations to isogeometric analysis, just as a topic in Web of Science, you'll find one in 2005, and now there are over 31,000 as of yesterday, or the day before. And the number last year was 8,144. So the subject has somewhat taken off. What it is, it's based on technologies from computational geometry that are used in design, animation, graphic art, visualization. You see these things every day. You see them in the movies. You see them in magazines and pictures, high-quality renderings. The technologies are NURBS, T-splines, subdivision surfaces, et cetera. And if you build analysis within the functions that are used in design, what you find is that you will actually be able to represent all of finite element analysis as special cases, but there are many other possibilities. First of all, you can do very precise and efficient geometric modeling. It can, in many cases, simplify mesh refinement, mesh modeling and refinement, and de-refinement. And I'll show some examples of that. And what's more, the real sweet spot in isogeometric analysis is smooth basis functions with compact support. I'll emphasize the word smooth. First, the most obvious thing, that allows you to solve higher order partial differential equations directly with simple Galerkin-like procedures without additional embellishments and mixed methods and things of that nature. You also find you have superior approximation properties, and I'll show you some examples of that. And of course, it facilitates the integration of design and analysis. So if you think of isogeometric analysis as an analysis technology that somehow is related to finite element analysis, you see that it really subsumes the usual techniques in finite element analysis: mesh refinement, H refinement, polynomial refinement on a fixed mesh. But again, the sweet spot is out here, where you actually raise the order, but you also raise the smoothness simultaneously. So our most desired technologies are when you use optimally smooth spline basis functions. So in way of tutorial, if you're not familiar with splines and NURBS, I'll say a few words about them before getting into more interesting things. Splines are usually developed first in one dimension, and then you use tensor products to put together the other dimensions. So you start in one dimension. You have a patch or an interval subdivided into knot spans. And these are the knots, just the locations of points in that interval. And you start off with constants, piecewise constants, and then you can use the so-called Cox-de Boer recursion relationship to generate linear functions from the constants. You put the linears on the right-hand side, you generate quadratics, and so on and so forth. And if you do that for a uniform knot vector, you would get piecewise constants on the knot spans, as you see. Then you'd get the linears of finite element analysis. When you go to quadratics, things change compared with finite element analysis. You can see sort of the pattern here. Each order increase, you're increasing the support. You're also increasing the smoothness. You're going from C-1 to C0 to C1. And if we went to cubics, they would naturally be C2. And you notice another thing. They're pointwise positive. Again, unlike finite element functions typically. So here's a patch, and this has some of the flavor of what you see in practice. This is a non-uniform knot vector because at this point we've repeated a knot. And when you repeat a knot, you reduce smoothness. So these are quadratics. They are naturally C1 smooth, but when you've repeated that knot, now it's C0 at this point. If I repeat it once more, I will split the patch in two, make them completely discontinuous. Now, this utilizes open knot vectors. Open means at the end of the patch, you have multiplicity p plus 1. And then the functions become interpolatory at that point and that point. So if you take those basis functions and you multiply by coordinates, so-called control points, you can generate a geometrical object like this. Each one of these points is multiplying one of these basis functions. So you see, first of all, it's not interpolatory. And it's only interpolatory at the endpoints and at this point right here, where your C0 continuous. Now, there's a dual point of view here, too. This is the design point of view. If I tug on a control point, I will change the design monotonically. Obviously, that's what you want in design. You don't want oscillations. When you're dealing with higher order C0 finite element functions, if you start moving a point, you can create oscillations. Now, this is the finite element point of view of the design. You can deconstruct the design by way of Bezier extraction into Bezier elements, and they play the role of elements in isogeometric analysis. And in fact, you can do everything that you usually do once you understand the concept of Bezier extraction. There's an extraction operator that facilitates this. It's just a matrix. So you have a finite element point of view of design, and you also have the classical design point of view, which utilizes the let's say the global basis functions here. Here you'd be dealing with polynomials on each individual element. You can refine simply by introducing knots, as you see here. Now, the interesting thing about refinement here is that the geometry and the parameterization do not change during refinement. You don't have to search for the geometry to do a refinement that respects the geometry. You have, from the get-go, the exact geometry. And you're embedded in it when you refine or de-refine. And you can take this further and further to your heart's content. You can start all over and do p-refinement, keep the continuity the same, but introduce higher order basis functions. Now we have cubics, now we have quartics, et cetera, with the same mesh. In engineering, the most commonly used technology is NURBS. NURBS are non-uniform rational B-splines. They are ratios of B-splines. These are objects that have been constructed with NURBS. And what you see here is very precise representation of circles and conic sections. And that's because all conics are exactly represented within NURBS. For example, you can construct a circle taking 4 quadratic arcs. You do a projective transformation from one space dimension higher, say into the plane. You get an explicit formula for a circle, not an implicit formula. And then you can take a tensor product of that, create a torus. This is a 16-element quadratic torus. It's geometrically exact. And we can H refinement, in place again. The geometry never changes. Or we can P refine it. We go to cubics and quartics with the same fixed initial geometry. And you can go to 3D, as indicated here. Now, standard finite element analysis and NURBS-based isogeometric analysis share many features. One is the functions have compact support. They satisfy a partition of unity. They possess affine covariance, meaning if you move the nodes or if you move the control points, according to an affine transformation, then every point in the object respects that. If you invoke the isoparametric concept, as you often do in mechanics, where you have the displacements and the geometry represented by the same basis functions, then all patch tests will be a priori satisfied, despite the fact that you're working with rational functions. And again, that scares some people with a classical finite element background, but you can get optimal error estimates in Sobolev norms. And that began with work that we did some years ago at Giancarlo Sangalli, who's sitting over here, and other colleagues and students. And if you look at this error estimate for the basic approximation result for H-refined NURBS, it looks very much like a finite element result. The only thing that would change here as you refine the mesh would be H, the size of the elements, because the geometrical map, this is the geometrical map, is absolutely fixed during the refinement. It's independent of the mesh on that refinement. And this is the function you're trying to approximate. And there have been many, many works that have enriched that subject. So that's the functional analysis point of view. So what does it mean? Well, in way of an example, if we took a classical elasticity problem of a circular hole and an infinite plate, and you put it at tension of a value 10 in the x direction at infinity, and you H-refine away, these are the meshes. Now these are NURBS because that's an exact circle. These are not B-splines, these are NURBS. So you start with two elements, and you have fine mesh here. The geometry map, again, is fixed once and for all throughout that. It never changes. This is just that two-element mesh all the way up to mesh 5, and you can see the classical stress concentration of a factor of 3 is attained right at this point here. You're pulling in this direction. Now, what does it mean as far as convergence? Well, if you're doing a study in the literature and you want to plot up a result for this, you'd plot a curve like this, where you have the L2 norm of stress or the H1 norm. They're equivalent. And what you would hope to get, and you do, of course, is quadratic convergence for quadratic NURBS, cubic for cubics, and quartic for quartics. And you see you get the asymptotic rates, and everything's nice. But in this process, of course, you're increasing the number of degrees of freedom. That's H refinement. Now, K refinement, in some sense, is going in the perpendicular direction. What you're doing is you pick a mesh, you work on the same mesh, you don't change the mesh, you just order elevate and increase smoothness. And by virtue of the fact that you increase smoothness, you don't increase the number of degrees of freedom. You're essentially dropping from curve to curve here just by order elevating and simultaneously increasing smoothness, and you get no additional degrees of freedom except at the boundary. And look at you're improving accuracy, say, by an order of magnitude or more in a drop. So this is the magic, and I want to stress that smoothness is really the key to all of the good results that you'll hear about in this subject. And some of the fast methods now, too, rely heavily on smoothness. But globally, these functions are very different. They're not interpolatory functions, as are Lagrange polynomials, which are sort of standard functions in finite element analysis. Here, if you try to represent discontinuous data and you interpolate it, no matter how many points you will use, you'll still get these overshoots and undershoots. The amplitude will never decrease, just the wavelength will change. But here with NURBS, if you view these as control points, what you get is a monotone fit. You get actually smoother with higher order. And in fact, that actually does translate into robustness in practice. This is a square tube buckling problem, elastic plastic buckling. You jam this into a wall at very, very high speed, and you go into an accordion mode, as you'll see in a moment. This is a classic problem in crash worthiness. And this was done in LS-DYNA, which used to be strictly a low-order code, but now it has isogeometric capabilities and other capabilities that are higher order. This is with C3 quartics. These are the Bezier elements. So the span of one of these quartics is over 5 of these Bezier elements. And you see you get a very nice result. It's very robust. The robustness actually increases with order here. It increases with order. unlike C0 finite element functions, which decrease with order typically. They are fragile. And that is one of the reasons they're not used in many of the high, hard problem classes that are exemplified by, say, crash dynamics, for example, where you get many high-mode inputs. So let's look quickly at spectral analysis to try to get some analytical insight into what I'm talking about. So this is just the second-order differential operator in one dimension, the eigenproblem. This is the variational formulation for it in a simple Galerkin approximation. Standard finite element error estimates for the eigenvalues, the eigenfunctions in the energy norm and in the L2 norm are given here. And these exponents are more or less optimal, except there is sort of an interpolatory condition, a smallness condition on the mesh. These are asymptotic again. They don't hold in the large. They hold for sufficiently refined modes. Now, to understand what's going on, you need some way of representing things for all the modes in the mesh you're working with, because all modes are present and they can participate in the solution. So this is the Pythagorean eigenvalue error theorem. It pertains to all modes. It relates the L2 norm error of the eigenfunction, the eigenvalue error, and the energy error of the eigenfunction. And it gives you a budget, and you can compute these different values. Now, why this is important is if you would do eigenfunction decomposition of an elliptic problem, a parabolic problem, or a hyperbolic problem, you can represent the errors completely in terms of these quantities, completely. And what you would expect, of course, these are C1 continuous B-splines, quadratic B-splines. What you would expect is to get low mode accuracy. This is the spectrum for an n-element mesh. If you increase n, you get the same picture if you just normalize by n. So this is the error in each mode. Say this is the 80th mode out of 100, for example, or the 800th out of 1,000. So this is the eigenvalue error. This is the L2 eigenfunction error, and this is the sum of the two in the sense of that representation. So that's about what you would expect. So you expect to get something similar with C0 continuous finite elements, but you get some big surprises. It's well known that the eigenfunction, the eigenvalue error is composed of two branches in this case. One is an optical branch, and there's no approximability in this part of the spectrum. But the eigenfunction errors are even more bizarre. You get a spike right in the middle of the spectrum, and this is real. Now, in an elliptic problem, the higher modes typically are attenuated due to elliptic regularity and stability. In parabolic problems, if you wait long enough, they'll be attenuated. But in hyperbolic problems, if you tickle that mode, that error is there and it propagates and it never goes away. So these things are serious. And this is why in hard problems, functions like this are rarely used, because you will tickle modes like that. Now, if you go to higher order, you expect improvement. So this is C2 continuous B-splines. And indeed, you get improvement. Here, the accuracy was maybe 40% of the spectrum. It was very, very good. Now you're up to almost 60% of the spectrum, you see? Now you expect improvement also for the finite elements. But actually, things are getting worse. The optical branch here is diverging with P. And if you go now to C3 continuous cortex, again, you see improvement here. And here, you're really diverging. The sum of these two errors now is up about here. And what we found early on when we first started looking at the eigenfunction spectrum, these are the frequencies, the square root of the eigenvalues. This optical branch diverges with P. You have no approximability. You have a lack of robustness due to these bad functions and poor conditioning. And this is NURBS. Basically, the bulk of the spectrum is converging, as you can see. These are linear finite elements. Linear finite elements and linear B-splines are exactly the same thing. Why are they robust? No optical branches, no bad guys to cause disaster. This perhaps explains analytically why they're used so much in difficult problem-solving environments. So a few applications now. Let's look at wind turbines first. This sort of represents the confluence of a design package and an analysis procedure. This is a Rhino, which is a NURBS-based design CAD system. This is representative of Grasshopper, a visual programming language. And you can see what you're doing is you're parametrically representing the design, and then you're changing the parameters and visualizing how it affects the design. So you build your design in this environment. This is complicated. This is a real structure. It has many different materials, and all of the materials are stacked in composite layers. And so this is the real design. It's done now. It's complicated. That's your analysis code. I mean, that's your analysis file. You compute with that in isogeometric analysis. And the design code gives you the critical buckling mode, basically to engineering accuracy without any further refinement. If you refine, you can refine to your heart's content. Nothing's changing. This is the same structure analyzed at Sandia National Labs with ANSYS, with a 4-node shell with 6 degrees of freedom per node. This is done with a rotation-free shell. You don't need rotations when you have smooth basis functions. So you only have 3 degrees of freedom per element here. So for equal numbers of elements, these have even half as many degrees of freedom. The size of this problem is about 1/1000th of the size of the converged result with the existing commercial technology. The speed up is enormous, obviously. These are the kind of things we see with these technologies. Let me give you an example of the first patient-specific prostate tumor model. We published this in Proceedings of the National Academy of Sciences in late 2016. We're continually developing these ideas right now. But here, the key analytical technology is, this is all, again, NURBS-based. This is a prostate. This is a seeded tumor. It's going to evolve. And the key thing is the interface between the tumor and the healthy tissue. So you need adaptive refinement and de-refinement to do these efficiently. There are 4 hierarchical levels here. And all of that refinement is embedded in the geometry. You're never changing the geometrical map of the tumor, of the prostate. So that's an anterior view. Here's a posterior view. Again, you're getting very, very sharp interfaces by refining and de-refining. It's a little hard to see exactly what's going on there, so I have a couple of toy problems which illustrate it. This is one in 2D. This is the 5th level. The 4th level is this orange zone here. And this is the 3rd level, the 2nd level, and the 1st level. And you see how the refinement moved through the mesh, and then the de-refinement followed it. And then you can get these interfaces quite nicely. And the same idea with sort of a toy problem in 3D. Again, seeing quite nice resolution and efficient solution. So hierarchical embedded refinement is a very powerful tool here. And again, you never change the geometry as you do that. Here's an application to boiling. It utilizes the Navier-Stokes-Korteweg equations. These govern liquid-vapor 2-phase flows. The interesting feature of the Korteweg stresses is that they involve 3rd-order spatial derivatives. So if you want a simple Galerkin-type method for solving these equations, you need smooth basis functions. And so the calculations here are done with C1 continuous B-splines. So this is 3-dimensional boiling. This is a pool of water. This is the free surface. There's a cool plate up at the top. The water is heated on the bottom. These are density profiles. You begin to create little thermal plumes of vapor. So vapor nucleates at the bottom. It passes through the free surface, and then it recondenses at the top. And then you'll see in an animation in a moment how these droplets coalesce, and then they fall back into the fluid. This is the same calculation, but this is temperature contours. You can see some of the richness and the hot vapor plumes that are formed. You can see them perhaps more clearly here. This is the droplets that have coalesced at the top. So this is an animation. You can see the vapor plumes. You can see the richness of the details down at the bottom. Go through, the droplets form, they coalesce, they start to plop down in the fluid. And all that's done with a simple Galerkin formulation, but with C1 continuous splines. Now, one of the problems you have to face in the area of patches is the trim problem. The analytic version of this is immersion or immersed methods. They've come under a lot of interest in recent years in both finite elements and in isogeometric analysis. But these methods are, at least in the analysis sector, they go back many, many years. Some of the early work of Charles Peskin at Courant and others. So there's too many to mention, but I'll just mention there's some of the finite element and isogeometric people up here that have recently gotten into this. This is a fundamental problem that needs to be solved by isogeometric analysis, because this is what you dealt with from the CAD representation, and you have to compute in that. So in IGA, you're doing trim and immersion within the original CAD design geometry. So there are issues, of course, associated with that. You have cut cells. You have to do accurate integration. You have possible ill conditioning due to very small and sliver elements due to the cuts. And you have to accurately represent interface constraints and boundary conditions along the trim lines. So let's look at trim. Exactly what it is here's a tensor product patch. You put a trim curve in. It's just saying there's a hole there. The underlying parameterization is the tensor product patch. This is just a mask on the visualization. And you put pieces together, you trim files, and you glue them together. You don't really glue them together. In the CAD programs, they're not glued together at all. There are gaps and overlaps here, and they're not logically connected in any way. Topologically, they're connected, but they're not geometrically connected. So this is what you have to deal with. Now, there have been a number of works, and there continue to be more right now, trying to do the calculations directly in the trimmed NURBS context. This is the work, I'd say pioneering work, of Michael Breitenberger, who did his thesis under Kai-Uwe Bletzinger's mentorship at the Technical University of Munich. So this is a trimmed CAD file. This is it. You can see the knot structure of the trimmed CAD file. This is the untrimmed CAD file. This is the part that's been cut away of those regular patches. So the idea is to, well, take your design mesh. If you think it's not adequate for the analysis purposes, you can refine it to your heart's content just by inserting knots in the various patches. And again, that is all done within the exact geometry. And then you use these technologies of gluing those together along the trim lines and do the analysis directly in IGA in the CAD file. And this is just a comparison using that procedure. By the way, there's a plug-in that they've developed that is running in a number of CAD-like environments right now, and so you can actually use this. This is just a comparison. You can see sort of the smooth geometry in isogeometric analysis versus the more faceted geometry in finite element analysis. It's hard to say what the accuracy is because I don't think anyone really knows what the real solution here is, but it is certainly smoother and nicer looking. And one of the attributes is you can put the loads on. Of course, you do that in the analysis model is the CAD model. And then when you're done, if you've deformed it, if you were doing shape optimization, you don't have to figure out a way of getting the finite element results back into the CAD representation, which is a real problem. You are closing the loop here. You're in the CAD representation immediately. So you never leave it. Now, this is an interesting application of trimming that was done at Honda by Kenji Takada and his colleagues. They took a B-pillar, not the one I showed before, but another one. And this one has over 900 surface patches making it up, and many trim lines, obviously. And what they did is they replaced it by just mapping on one patch, one trimmed patch, very highly resolved, as you can see. And the holes represent trim curves here. And then just do just a solution of that one patch. So they just basically do that by L2 projection. And got amazingly good results in LS-DYNA, better than the finite element results that were more difficult to develop. So this was the IGA model. It took 20 minutes to do everything here. It took 2 hours with the conventional technologies. So I see this as another possibility. And when you think about a B-pillar is one piece of metal. It's cut. There are holes drilled into it. The boundaries are cut, shaped. Why shouldn't the CAD representation, the analysis representation, be one trimmed piece of mathematics, its counterpart? Well, you can do this also in multi-dimensions. You can use the idea of immersion. You take a CAD file. This is a T-spline. This is a watertight, unstructured spline representation of a design of a wheel. And if you want to do an analysis of that, you can drop it into a box of B-splines, throw away the elements that do not intersect the object, do adaptive refinement of the mesh in the areas that you're interested in particular, right here, and then develop, in this case, the finite cell method, which is developing a refined quadrature cells to integrate. And then you just compute on that. So this can be automated well. These are highly automatable type technologies. So this is sort of, you see the, let's say the finite element isogeometric analysis version of TRIM taken to 3D. And the final application I'll show are heart valves. What you see here is a so-called patient-specific aortic valve in a region of the aorta. This is the aortic root here. And the background here is a three-dimensional arterial wall. It's deforming. The fluid mesh is deforming in an Ale-type format, arbitrary Lagrangian Eulerian. This has a variational multi-scale solver. Everything is isogeometric. This is all compatible, smooth splines. And then the leaflets of the aortic valve are modeled with Kirchhoff-Love shell elements. Again, rotation-free shell elements. You don't need rotations because you have smooth basis functions. And you can see that there's a lot of technology here because you have this shell immersed, moving through a moving background mesh. Now, the design application here is actually to bioprosthetic heart valves. These are made from porcine or bovine tissues. And if you count up the number of times your heart beats in a year, you find it's over 30 million times. So these are used in valve replacement surgery. And they typically have a lifetime of about 10 to 15 years. And very often nowadays, as people live longer, if you need valve repair, you may need multiple valves in one location, which is obviously not something that's desirable. So the challenge is to increase valve lifetime. And a design capability was built for these. This is a jig that was actually used to experimentally validate it. The experimental jig conforms to this geometry. This is what the sort of the NURBS mesh looks like in the fluid domain and with the valve surfaces inside. And the way you use this, again, you have a deforming artery wall. That is absolutely essential in these calculations. There was all sorts of speculations why valves would flutter in calculations. And they were always done with rigid walls, but the speculations were due to material properties and all sorts of things that turned out to be bogus. It's just the deformability of the wall mitigates the flutter problem. But you can take various designs. These are NURBS-based designs. These are unstructured T-spline-based designs. And once you have your mesh for your fluid and your artery, you can just drop these in without changing the background mesh and compare designs for optimality. So with that, let me summarize, since I'm right on time, I guess. Isogeometric analysis has become one of the most active areas of finite element research and also computational geometry, CA, computer-aided geometric design research. The goal that we set out with in the beginning is improving engineering product design by speeding up the design through analysis interface. And I think that is taking place, and it continues to be improved, of course. The goal when you develop a technology is always better, faster, and cheaper. If you get one, that's good. If you get two, you probably have a success. But I think the opportunity here is to get all three. You can improve the quality of analysis quality and robustness. You can do faster model development in many cases, attain faster solutions, and thereby decrease cost. So it's a fruitful, promising, and growing area of research. And just lately, it seems to be gaining quite a bit of traction in industry. I've been in this business now engineering business for a little over 50 years. So I graduated from undergraduate school in 1965. I got interested a couple of years later in finite element analysis, and where I was working, the resistance to finite element analysis was absolutely ferocious. You would have thought I was the devil incarnate when I was proposing to develop that there. But we survived. In fact, as I reflect back, all of the things that I've done over the years, the ones that I think that I'm the most noted for, and I think have been my best work, were the ones where I was absolutely reviled initially for, isogeometric analysis being one of them now. Arthur Clarke has put this into a nice way as he has described new ideas going through 3 periods. Can't be done is the first period. The second is it probably can be done, but it's not worth doing. And the third one is I knew it was a good idea all along. Thank you very much for your attention, and please come here.
I've got the microphone to come bring to you. All right.
Hi. Thank you for a very inspiring talk. I'd be interested to know if there's what software tools there are that other people can use. For instance, I'm interested in surface representations for boundary integral. Can
Yes.
I go to, where can I find either your tools or other tools that let me represent a surface in this way, do refinements, and kind of what's the state of the open source software for this stuff? So.
Well, actually, to represent the surfaces, I mean, you can use standard CAD tools for boundary element analysis. For example, you could use, we mentioned Rhino a few times. It's a very lightweight, accessible NURBS modeling package. And you don't have to worry about the connectivity between the patches there in a boundary element formulation. You just need the patches themselves. Now, you do have to desensitize calculations for where you cut these things with slivers, as they will be in the CAD tool. Your patches will likely give rise to sliver elements if you have adjoining pieces. And you have to worry about the quadrature. Now, I don't know if there's any publicly available boundary element code, but for IGA, but there are a number of people working in this area because it's an obvious area. There's a very nice paper, a couple of papers written by a former visitor of mine, Benjamin Marasig, who's at Linz in Austria. And he is a boundary element guy and has really done very nice work on the trim problem and getting boundary element formulations to work in that context. So I would refer you to his work. There are 2 papers. There's one paper that's out, and there's a big paper on trim that's coming out in the Archive for Computational Engineering. It's already published online. It's an 80-page paper. Sort of the subtitle is what you always wanted to know about trim, but it's all in the context of boundary elements.
So thank you for this very lucid and inspiring talk. So one point you had in repeated case studies that you had shown, you had shell elements, solids, coupled sometimes with fluidics. And you repeatedly mentioned that rotation degree of freedom are not necessary, of course, because of the high conformity.
For the Kirchhoff-Love shell model, which is the thin model.
So my question is, what is your take on membrane locking in
membrane
shells?
bending locking. My take is I'd like to see that problem solved.
Okay. Thank you. That was a succinct and clear.
It is the last open problem in computational shell analysis, and it afflicts not only thin shells, but thick shells as well. Yeah.
I see the other question. So I have a question for you, actually. Certainly, we've had a look at the eigenanalysis of the C0 systems and seen a lot of those properties. I think I'm right in saying, though, if you go to the DG extreme, we don't see such unusual properties. So we kind of have
DG,
this.
you see, okay.
And so
I'm glad you asked me that question.
Ultra.
All right, go to DG. Now with DG, what do you have? You have discontinuities. You would think the problem would be worse. What do you do in DG, though? Now, if you're doing an advection operator, the way you do DG, you do it in the stable way. You put it on the side of the element to give you basically an upwinding effect. And that stability produces a dissipation in your spectrum. And what you do is you basically wind up damping all those modes. Now, I'm not for or against DG. I use the technology when it's useful to me. But the point is, it's really hard in DG to beat a good CG code or a good smooth code because you're carrying all those modes and you've introduced a mechanism to kill all of those modes. It's not as efficient. Yeah. You need a lot of degrees of freedom.
All right, so efficiency versus, but the stabilization, the properties of their stabilization, which is interesting. So going weaker.
Well, we've looked, you know, again, I advocate people looking at spectra. We've looked at the spectrum of like Stokes operator by every, you know, element known to man that's BB stable and all. And I mean, DG, frankly, is the worst. Absolutely the worst.
Okay, I better be careful now. Right, we have a whole bunch of plenary sessions coming up on DG methods, and need to facilitate that happening. Okay, maybe we should thank our speaker once more and allow everyone to filter
You
out.
can see why I'm not such a popular guy, you know?
It was interesting.